So hello everyone. While Andrea fixes this issue with his computer, I will then continue with my presentation. My name is Marnik, and I am a postdoc at EPFL in the group of Professor Marsari. And I want to talk a bit in this presentation and also the presentation of next presenter Christian on some of the tools we've been developing within our group to actually manage workflows running Quant Espresso and also other simulation codes using a workflow manager which we call AiiDA. And so the main motivation for this work and all of the tools we've been developing is this issue of reproducibility in science. And this is some results here you can see from a Nature paper from some years ago, where basically scientists were asked if they thought there was an issue of reproducibility in science, basically reproducing your results at some later date. And it seems that the vast majority believes at least there is a slight crisis, and even the majority believes that there is a significant crisis. And if you ask scientists from different fields, if they have an issue producing someone else's results after some time, a lot of them says this is indeed the case, and even producing their own results after some time seems to be problematic for a lot of people, and I'm sure many of us have also experienced this. Now, in experimental research, you have to deal with samples, preparation, all of this. There may be some excuses why your results aren't reproducible, but in computational research, we should really be able to reproduce our results even after some time if you're running the same codes, same parameters, right? So the challenge here is to make our research more reproducible and open science easier. And so in our group, we've worked quite a bit on developing several tools in this context. The main tool I'll be talking about is AiiDA, the workflow manager I've already mentioned. And the next presentation, Christian will be talking about AiiDA Lab, which is a Jupyter-based web platform. So basically, that allows you to make a GUI for running workflows with AiiDA. And of course, also the Materials Cloud, which is a web platform for sharing your data according to the FAIR principles. And so AiiDA itself is, as I mentioned, a workflow manager with a high focus on being able to run workflows in high throughput, which I'll show in just a second, and also having the full provenance or history of the calculations stored. It's completely written in Python. It's completely open source, distributed under the MIT license on GitHub, at the link you can see here. And the main features here, which I'll go through step by step in the following slides, is a scalable workflow engine, automated full data provenance, a flexible plugin system, and then the built-in support for HPC. The last of which basically means that typically you will run AiiDA on your workstation and then run the workflows on different clusters. So AiiDA comes with built-in support for using SSH to do this, and also built-in support for several schedulers such as Slurm and Torque on the various clusters you have available. Now, as for the scalable workflow engine, we recently actually had a nice demonstration of AiiDA and how at what scale it can run on a new supercomputer here in Europe, the Lumi supercomputer based in Finland. We got exclusive access here to the Lumi C partition, basically the CPU partition, for about 12 hours during the pilot phase. And during this, so we used AiiDA. As you can see, initially, there was a bit of a startup time in order to get all the workflows running, but at some point we managed to stabilize it there pretty nicely and use the full machine for about 10 hours solidly. And this time we basically optimized around 15,000 structures using 55,000 Quant Espresso calculations. And also AiiDA comes with several error handler features. And these were handled basically on the fly for about 8,000 different calculations. And so this was basically a project where we also wanted to benchmark AiiDA, of course, but in order to get some scientific results, we ran some structure optimizations with previously PB-Sol, and this gave us a nice little comparison of PB and PB-Sol when it comes to the volume compared to experiment. The second feature, and I think one of the most important features of AiiDA is the data provenance. So the idea here is that for every calculation you run in your workflow, you want to keep track of the inputs and output nodes. So all the inputs of your calculations and all of the results of your calculations. And so AiiDA does this automatically once you've written a workflow. It will connect all of your different steps through the provenance, through this is directed acyclical graph, which basically allows you to go back and check for each calculation what your inputs were. And this, of course, is very important in the context of reproducibility, to be able to see in which step you used what inputs. And on the other hand, it also forces your data to be much more organized, which can be very useful if you come back to your project at some later time. If you just have all of your calculations in certain folders run through a bash script or something, it becomes tricky to analyze the data or get the data you need at some later point in time. So AiiDA really helps quite a bit in forcing you to organize your data in a database that's queryable and easy to basically extract the data that you're interested in. Now, if you install AiiDA, you will basically install the AiiDA core package, which just comes with the core functionality for running workflows and etc. But typically, you would also want to install certain plugins because AiiDA is very extensible in this regard. We have around here, I think this is also been updated. We now have over 80, 90 different plugin packages with different calculation plugins, workflows, etc. that are available for people to install. And one example, of course, here is, especially in the context of this school, the Quantum Espresso plugin for AiiDA. So if you install this plugin, you will have all the workflows available that I also showed previously and will show in the future. And so then you can start running AiiDA for using a Quantum Espresso. There's also, for example, another package which I'm maintaining, which is called AiiDA Pseudo, which allows you to install pseudo potentials such as the ones in the Pseudo Dojo or the SSP pseudo potentials easily and then use them for your calculations. So basically, once you start using AiiDA, you will install certain plugins, extend it, and then run your workflows for these specific plugin packages. Something else we've been working on in our group is what we call a protocol. So basically, when you're running all these calculations in high throughput, you don't want to do a full conversion study for each of the materials which you're investigating. Basically, what we've been trying to work on is a set of input parameters that will automatically determine a reasonable, let's say, input set that allows you to get a good precision for most of the structures that you're investigating. One example here is for the energy cutoffs. We rely here on the work of previous colleagues, Gianluca and Antimo, who've developed this standard solid set, the standard solid two potential set, which also come with suggested cutoffs for each of the elements. So based on this, we can basically determine the cutoffs to use. And then there's other work of previous colleagues, Niklas Horman, who has investigated for a set of a couple hundred reference structures, what should be, for example, the correct K-point density you want to use in order to make sure that, if, for example, in the case of total energy, around 95% of your structures are within a certain precision, right? So basically, by doing this, we can run all of our calculations using these protocols without having to do a conversion study for these kind of input parameters for each of the structures. And so as the final part of my presentation, I'll just give a quick example of a project which we've been working on using these tools. And that is what we call the MC3D. Basically, it's a three-dimensional crystal database project, where on the one hand, we want to start from basically only experimentally known structures in the three different databases, which you can see here, the polling file or MPDS, the ICSD, and the COD. The interesting aspect here is that compared to other databases, we also include the polling file, so we hope to find some interesting new structures there. We also want to ensure reproducibility by on the one hand using completely open source codes, of course, like Quantum Espresso and AiiDA itself. And then, of course, we also want to have the full history of our calculations of provenance, running all of our calculations through AiiDA. The final argument for this project was also to increase a bit of the, let's say, the database biodiversity, because other commonly known databases in the literature are Material Projects and Atholib, typically rely on vast as their code, and we'll be using Quantum Espresso. And so it will be a nice verification project to see, you know, if all these different databases produce the same results for different structures. So what we did here, and this was mainly work done by Sebastian, one of our colleagues, we started from around 900,000 experimental structures extracted from these databases, and then we used a little AiiDA workflow called the SIF clean workchain that basically first fixes some syntax issues, removes unnecessary tags, basically cleans up the SIF file, and then it normalizes and primitivizes the structure using the SeqPath tool, also available on Materials Cloud, in order to obtain about 860,000 structures for which this whole process was successful. We then remove non-stoichiometric structures and finally use PyMatGen structure matcher utility to then remove also duplicate structures. So we're only running unique structures in the end. And so based on this, we then get a set of different structures. We continue to run using AiiDA workflows in order to optimize geometry and obtain our structured database. And so I won't go into too much detail here, but basically in the main workflow here, we have two different steps. We first have a reconnaissance SCF that basically tries to flag if structures are magnetic or not, and hence requires spin polarized calculations. And then we go to the structure optimization workflow, which I've already shown previously. One nice feature that I've already mentioned as well is that there is the possibility of setting up error handlers for basically automatically recovering your calculations in case it fails. An example is, at some point it's possible that your electronic conversions fails. Then you get an exit code 401 from your calculation. And basically the AiiDA workflow that takes care of this error handler error handling functionality, we'll then simply, for example, change a bit the charge density mixing, and hopefully the next step you will have a successful calculation. And so here you can again see this workflow I already showed before, where in the initial step you have the relaxation. The initial calculation failed, but then it was restarted. The second calculation was fortunately successful. It then moves on to a next relaxation step, and finally a final SCF for calculating the charge densities. And so this structured data set we have already completed around 35,000 relaxations of, which are available on the Materials Cloud as the MC3D. And so from this basic database, we've started several other scientific projects. We are now calculating band structures and projected density of states. We're also using these structures as charge densities to do an automated memorization. This is mainly a project of a colleague in Feng. And then there's also a project by my colleague Francisco to use basically the charge densities we calculated to search for new electrodes. And I myself am also now working on new projects related to superconductors. So basically, we want to use this platform and this database as a starting point for several scientific projects. So that's it for me. I will now pass the word to my colleague Christian, who will be talking a bit more about the other tools I mentioned, such as AiiDA Lab and Materials Cloud. So Christian, the floor is yours.
Thank you very much, Marnik.